Hello, students. All right, today we are in the lesson 4.3, part 1 here. Okay, we have learned about what an integral is. Okay, we've learned about is finding the area underneath the curve, and this is going to lead into an idea. We're about to make a connection today. Okay, we're going to make a connection today with the area underneath the curve with something. And this is literally called the fundamental theorem of calculus. And there's two parts to it, and we're looking at part 1 today. Okay? So I've approached this multiple ways in the past. I would like to try this today. Okay, we're going to do a warm-up. Let's see if we can make a connection here. It says, find the area underneath the curve, y equals x squared from 0 to b. Okay? 0 to b. So just to kind of give a little sketch of what I'm talking about. X squared is this graph right here, right? And if I'm saying we're going from 0 all the way over to b, and b is just an arbitrary point. It could be 1, 2, 3. It could be 1,000. Okay. Let's say we're doing that. Now, the only way we know how to find the area underneath the curve is to use the definition of an integral. Right? So remember, that's the limit as n approaches infinity of b minus a over n summation I equals 1, not n, I equals 1 to n of f of a plus b minus a over n I. Okay. So let's plug in everything. A is 0 and B is B. Okay, so we don't have a number for B. So what we're going to have is the limit as n is approaching infinity of B for B minus 0 over n summation I equals 1 to n. And this is f of 0 plus b minus a, or b minus 0, is b over ni. So I'm going to go ahead and plug in 0 plus b over ni into the function. So which is literally going to look like b over ni squared. Okay. So we did we plugged in a plus b minus a over ni into the function x squared, and that's what we're left with. Okay. So we got the setup. Let's go through and see what the final answer is going to be. And remember, b is just a number, n is just a number. Let's see what we got. Okay. So I got the limit. N approaches infinity. I got b over n summation I equals 1 to n. And this simplifies to b squared over n squared I squared. Okay, so we distributed. And now the next step would be to separate, which there's only one term, so we don't need to separate. So what I can do instead is just go ahead and take out the constant b squared over n squared. I can take that out and then do my identities. Okay? So I got the limit as n approaches infinity of b over n times b squared over n squared. And I'm left with the summation I equals 1 to n of I squared. Which, the whole point of doing that is I have an identity for that. Okay? So let's see what we got here. We got the limit as n approaches infinity. Those two terms combine to b cubed over n cubed. And the identity for the summation is going to be, it's I squared, so that one's going to be n plus 1, 2n plus 1, all over 6. Okay. And then remember the limit. So this is just one fraction, right? This is just one fraction. So the limit is just going to be doing our end behavior rules. So let's think about what the leading terms on top and bottom are. On bottom, it's 6n cubed. And on top, it's b cubed n 2n. So in this case, that would be 2b cubed n cubed. Okay, that would be our leading term if we were to multiply everything out. And because it's the same power on top and bottom for n, we take the leading coefficients, okay, which is 2b cubed over 6. So this area underneath this curve is equal to 2b cubed over 6, or another way of saying that is 1/3 b cubed. Okay? 1/3 b cubed. The area underneath the curve is equal to 1/3 b cubed. Okay. Now, what if I called that b an x? What if I made that b an x? What if I rewrote it this way? What if I said 1/3 x cubed? Do you see a relationship? So this is just an arbitrary point b, right? This could be any value. Do you see a relationship between y equals x squared and 1/3 x cubed? See a relationship between those two? What if I were to take the derivative of 1/3 x cubed? What would I be left with? 3 comes down, 3, so that would just be x to the power of 2. Wouldn't that just be back with where I started? That is a pretty interesting idea. So what we just showed is that I took the area underneath the curve. I did the integral, I guess is the way of saying that. I took the integration of this function to some arbitrary point b, and I'm left with 1/3 x cubed. If I take the derivative of that, I'm back to where I started. What could that mean? Could it mean that taking the integral is just working backwards from taking the derivative? Let's try another example. Find the area under the curve, y equals x, from 0 to b. So like if I write this out with the integral notation, that's the integral from 0 to b of x dx, which I know is equal to the limit as n approaches infinity of b minus a, or b minus 0 over n, summation I equals 1 to n of f of, and I'm not even going to put the f of because we're just literally plugging it into x. So it's just going to be the actual value itself, right? I'm literally just plugging b minus a over n, I plus a in for x. So literally it's just going to be 0 plus b minus a over n I. Okay. So I'm finding the area underneath the curve from 0 to b. Now, I want you to go, like, before we even finish this problem, I want you to think about what this is going to be, but based off of our answer from before. What do you think that's going to be? Let's figure it out. So the integration 0 to b of x dx is equal to. All right, we're going down the steps. I'm going to do this. I'm going to say the limit as n approaches infinity. And all I'm left with on the inside here is b over ni. I'm going to go ahead and bring that b over n out. And I'm going to say b squared over n squared. So when I combined it with that. And I'm left with the summation I equals 1 to n of just I. Okay. All right, well, our identity for I is equal to, well, we know what that's equal to. We got b squared over n squared times I is just n plus 1 over 2. Okay. So if I take this limit of this single rational here, the leading term on top is b squared n squared, and the leading term on bottom is 2n squared. Because we have the same power on top and bottom, that means I'm left with b squared over 2. So what I'm saying here is that the integral from 0 to b of x dx is equal to 1/2 b squared. 1/2 b squared. So if I go from 0 to b, it's 1/2 b squared. Interesting. What if I replace that b with an x for the point of this argument here? What if I said 1/2 x squared? What if I take the derivative of that? What am I left with? Well, x. So what does that mean? Does that mean taking the integral of a function is the same thing as going backwards from derivatives? Yes. Yes, it is. That's the connection I want us to make. If I take the integral of a function, and it's going to turn out, it does not matter what this number is right here. It will not matter what that number is right there. If I take the integral of a function to some variable, excuse me, and then if I take the derivative of that, I'm back with where I started. Do you see that I'm back with where I started? So if I integrate and then take the derivative, I'm back with where I started. That must mean that this is doing that an integral is the reverse of doing a derivative. It's working backwards. Another name that I'm going to use for that is an integral is called an antiderivative. An integral is literally undoing a derivative. It is the antiderivative. So we're gonna learn this throughout the days that taking the integral and taking the derivative is just going back and forth between each other. And that is the fundamental theorem of calculus part 1, is the connection between integrals and derivatives. Now I chose to explore that by showing a couple basic examples. The integration of x and the integration of x squared. At one point there was a little exploration activity I did using this graph and using this graph. But I don't think it's beneficial for us. I think that new warm-up is the better way to go. Okay? So I'm going to use that to lead into, now there's two parts to this, okay? And I want to lead in, and we're just talking about the fundamental theorem of calculus part 1, or I'll say a lot, FTC part 1. Okay, FTC part 1. It states literally the connection we just made for warm-up. Let me show you what it means. It says if f is continuous on a to b. If f is continuous on a to b, like we've seen with taking the area underneath the curve, then the function g, defined by this, so let's say we call g the integral from some number to x of f of u du, where x is between a and b. Okay. It is also continuous on a to b and differentiable on a to b. And then here is what FTC part 1 says. That if I were to take the derivative of this, meaning if I were to take the derivative of the integral, if I were to take the derivative of the integral, it's like an inverse function. The derivative is going to undo the integral. So another way of saying this right here is to say, okay, if I take the derivative of an integral, right, from a to x of f of u du, the derivative and the integral are going to cross each other out, and I'm just left with f of x. So literally, g prime, which is the derivative of the integral, is going to be equal to f of x. That literally explains antiderivatives, how taking the derivative of an integral makes it go away. Now, the reason that I have u here, du, is because I want it to be another variable other than x, because x is being plugged in, so I chose another variable. Let's look at some basic examples of how this works in practice. Okay, look at this. This says find g prime if g is the integral from 0 to x of the square root of fa squared plus 1 dA. What this means, how we know, what we interpret this as, is finding the area underneath the curve of this function from 0 to x. But then it's saying to actually find g prime. So what it's wanting me to do is to take the derivative of this. Now you can find the integral and then you can take the derivative if you want. But what we learned from the warm-up is that if we were to take the integral and then take the derivative, we would just be back to where we started, because a derivative is the opposite of an integral. So simply put, if I were to take this integral, then take this derivative, I would be left with my original function. My final answer here is 5x squared plus 1. So it would be like plugging x in for a. If I integrate it, I would get a function. But if I derive it, I would be back with where I started, just like we showed in the warm-up. That's FTC part 1. By FTC part 1. If you ever take the derivative of an integral, it's because of FTC part 1 that works. And you should probably state that, especially if it's a free response. Let's look at another example. So I got the function defined as the integral. So g of x is the integral from 0 to x of a cubed plus a squared minus 5dA. So what this means is that I'm defining a function. Like I want to kind of draw out what this means real quick. Like here's 0, and let's say like it goes all the way over to a, whatever. Or actually, we're already using a as a variable. Let's call this b then. This is a cubic, which means, I don't know, my function is doing something like this, whatever. What g of x defines is whatever x value I plug in, let's say I plug in 3 for x. It means to find the area underneath the curve from 0 to 3. So I'm literally just defining an integral as a function. So like whatever x is going to make the area change. The connection we made in the warm-up, this is the cool part, is that if I take the derivative of this function, if I were to take the derivative of this, I would be back to where I started. I integrate it, then I derive it, and I'm back to where I started. You see, we're so used to doing integrals like to an exact point, exact value, but we've never introduced a variable x in the integral before. If I introduce a variable x in the integral, I have a function. And if I take the derivative of that function, I'm back to where I started. It's literally just inverses. They undo each other. That's the relationship. So if I take the derivative of this, which is what it's asking me to do, I'm going to be back to where I started. I'm going to be back with x cubed plus x squared minus 5. Taking the derivative of an integral takes you back to where you started. This is by FTC part 1. All right. Find the derivative of the integral of secant t dt. Derivative of an integral, okay, the derivative of an integral undoes it. It leaves us with where we started. Now the only difference is that if I were to like take the integral of this, okay, I'd be plugging in 1 and I'd be plugging in x to the 4th. And if I had x to the 4th plugged into this, and then I took the derivative of x to the 4th inside secant, by chain rule, you would be taking the derivative of the inside. So here's another little thing to keep in mind, is if I take the integral and then I take the derivative, yes, I'm back to where I started, but because I'm taking the derivative, it's going to be chain rule. So if there's anything other than x in the integral, you have to multiply by the derivative of the inside. So, all right, so the derivative of the integral leaves me with where I started, okay, but with x to the 4th plugged in. And by chain rule, since that's something other than x, we actually have to multiply by the derivative of the inside. So this is really what I'm left with. The original function, but with a little bit of a chain rule through it. That's it. FTC part 1 states that a derivative is related to an integral by undoing it, by being the opposite. All right, I got 3 more examples. Shoot, I may go through all 3. Let's see, only have 19 minutes. All right, so how we do this? Okay. Now, in order to do FTC part 1, in order to take the derivative of an integral, it's got to be in the form a number to a function. So usually we see that 0 to x, but it's not always that case. So in this case here, like in order to take the derivative of the integral, it's got to be in the correct form. We got to be going in the correct direction. In this case, we're not. The function has to be on top. So in this case, before I take it, I'm going to rewrite y as the negative integral from 1 to 1 minus 3x of u cubed over 1 plus u squared. And then if I take the derivative of this, okay, if I take the derivative, so if this says to find y prime, I am taking the derivative of negative 1 to 1 minus 3x of u cubed 1 plus u squared. Okay? And if I take the derivative of the integral, it cancels it out, and I'm left with what I started. But because I have something other than x here by chain rule, you have to multiply by the derivative of the inside. So what I'm left with is negative, because it's negative, u cubed, or 1 minus 3x cubed, over 1 plus, instead of u squared, 1 minus 3x quantity squared. But by chain rule, we need to multiply by the derivative of the inside, which the derivative of the inside is negative 3. That's it. Let's try the next one. The next one is, if I'm trying to find y, okay, so first of all, y is equal to, or I guess we'll go ahead and say y prime, is equal to the derivative, and I need to rewrite this as negative 0 to 1 over x squared of sine t cubed dt. Okay. So I rewrote the integral by flipping it, and I just said sine t cubed. Okay. Now again, taking the derivative of this beauty takes the derivative and the integral, makes them go bye-bye. They undo each other. If I take the integral and I take the derivative, I'm back where I started. So what I'm left with is negative, okay? And instead of a sine of t, it's going to be the sine of 1 over x squared cubed. Okay? But because that's something other than x, I'm going to multiply by the derivative of the inside. And the derivative of 1 over x squared, if you do that, is negative 2x to the negative third. And that is by FTC part 1. By FTC part 1. Okay. All right. I'm going to save this one. We're at 22 minutes. I'm going to save this one for class. I would like to do one example in class together. This is not hard. For those that want to try it on your own, look at my notes, but I want you to keep this in mind. Well, actually, you know what? No, I'm gonna wait to explain this one in class. But I want us to understand again what we learned today. We just made a huge connection. We have learned derivatives and we have learned integrals. What we just did is we showed that they are related to each other. That an integral is something called an antiderivative. It is the working backwards from derivatives, which is a very, very cool idea. And in our next lesson, we're going to learn Fundamental Theorem of Calculus Part 2, which y'all will like even better than Part 1, because now that we have this connection, Part 2 is what introduces our shortcut rules for the definition of an integral. So you're going to love that a lot. All right. Good job, guys. We'll finish this tomorrow in class, and I hope you'll have a great day.